Bismillahirrahmanirrahim. Welcome to the YouTube channel Electrical Engineering. This is the second lecture on magnetic circuits, which is a content which will be discussed in DC machines, lecture videos. And in this lecture, I will demonstrate some more problems on magnetic circuits. In the first lecture, I discussed introductory content with you with one or two examples. And in today's lecture, I will show how to solve complex magnetic circuit problems. So this is the circuit which is the first problem. Okay, and these problems are taken from these lecture notes. Okay, the problem statement of this circuit is given here. A two-legged core is shown in the figure. The winding on the left leg has 600 turns and the winding on the right has 200 turns. The coils are wound in the directions shown in the figure. If the dimensions are as shown, then what flux will be produced by currents I1 and I2? Assume relative permeability as 1000 and it is constant. Okay, so the dimensions of this core are given, and this is a square shape core because we can see identical dimensions are seen along the vertical and the horizontal axis. The depth of the core is given as 15 centimeters. So first of all, we have to calculate the reluctance of the core, and the reluctance is given by L over mu. A L is the total length of the core through which the flux will flow. Mu is the permeability, and A is the cross-sectional area of the core. So the area is calculated as 15 multiplied by 15 centimeter square. Since we can see that the mean path length, which is calculated from the midpoint of each leg, is 65. Okay, so 15 centimeter is the total width, but the half of the width will be 7.5, and similarly 7.5 centimeter will be over here. So 15 plus 50 is equal to 65. So 65 multiplied by 4 will be the total length of the core. So by using these values in this expression, the calculated reluctance is 92 into 10 to 3 ampere turns per Weber. And now we have to draw the electrical equivalent circuit of this core, and this can be drawn as two electrical or EMF sources, and they are connected, and there is a resistance R in between them, and R represents the reluctance of the core, and these two sources correspond to the sources of magnetomotive force. Now, by analyzing the sense of the winding, the resultant flux will flow in the upward direction for this leg, and by analyzing the sense of winding at this leg, the direction of flow of flux will be downward. So the resultant polarity of these EMF or MMF sources will be kept as this, so plus minus, so that the resultant flux will leave the positive terminal and will enter the negative terminal. So flux leaving at this branch will be upward and flux leaving at this branch will be downward, as can be observed by these sense of windings in this figure. So this is the total reluctance. Now the total flux will be calculated as N1 I1 plus N2 I2 divided by R, because these two MMF sources are reinforcing each other, because the direction of flow of flux from both these sources is the same. And so that's why these MMFs will be added together, and the value of the total MMF will be divided by the reluctance. So the net flux is given as 0.0054. So now we are moving towards the second problem, and the problem statement of the second example is given in this slide. So this is a ferromagnetic core, and we have a winding at the central leg, and this is a ferromagnetic core. Its relative permeability is given as 2000, and 300 turns are available for this winding, and there is an air gap of 0.05 centimeter for the left leg, and there is an air gap of 0.07 centimeters for the right leg, and 7 centimeter is the width of each branch, and the length of this branch is 30 centimeters. So we have to calculate the flux At each branch means the central branch, left branch, and the right branch. And then we have to calculate the flux density in each air gap. So this problem is also not very difficult, and all these dimensions are given. So first of all, we have to draw the electrical equivalent circuit of this core, and now we can see there are two separate reluctances for the left branch and for the right branch. One reluctance corresponds to the reluctance of the core, and the second reluctance corresponds to the reluctance of this air gap. Since the relative permeability of this air gap and the core are different, so they will be represented by two separate reluctances. But in the middle or in the central branch, there is no air gap, so we can represent the reluctance RC, which is central reluctance of the central branch, and this corresponds to the MMF source. So the reluctance at the left branch is calculated using this expression. Now we can see that there are three lengths. Okay, so uh, one length is this, one length is this, and one length is this, and all these lengths are equal to 37 centimeters. So that will be multiplied by 3, and the centimeters are converted to meters, and relative permeability multiplied by absolute permeability and multiplied by 7 into 7. This is the cross sectional area of the core. Similarly, we can calculate the reluctance of the right branch, and all these parameters are same for the right branch as well, so the same value is obtained. Now we have to calculate the reluctance of the central branch. Now the central branch length is 37 centimeters, so by using this value, the central branch reluctance is calculated as 30 into 10 raised to power 3 ampere turns per Weber. Now the reluctance of the left gap will be calculated. The length of the left air gap is 0.05 centimeters, and the permeability of the air gap is mu naught, which is 4 pi into 10 to minus 7, and this is 7 into 7. So the reluctance of the air gap is also calculated for the left branch and for the right branch. Then we will calculate the equivalent reluctance, and since our source is present at the central branch, so the reluctance will be calculated accordingly, assuming that the flux is leaving from this branch and it will be divided into the left and the right branches. So this branch and this branch, they are connected in parallel, and their combination is connected in series with the central branch. So the equivalent reluctance will be equal to RC plus RL plus RGL parallel with RR plus RGR. So this is the equivalent reluctance. Then we will calculate the flux at the central branch by using this expression, and this is the flux leaving through the central branch. Now the flux at the left branch and the right branch will be calculated using current divider rule. So here we will assume flux divider rule, and at the right branch the flux will be equal to the left branch reluctance divided by the total reluctance multiplied by the total flux or the flux at the central branch, and vice versa for the left side. So these are the values of these fluxes. Then we can easily calculate the flux densities, and flux density is equal to total flux divided by the cross sectional area. Since the cross sectional area is 49 into 10 to minus 4 meter squares, so by using the values of the fluxes, we can calculate the values for the flux densities for the three branches. Now we are moving towards the problem number 6. So the problem statement of the sixth question can be found over here. And this is a little bit complicated circuit in which we can see a winding on the left branch, a winding on the central branch, and winding at the lower right branch. Now this is an ideal core, so the relative permeability is given as infinity, which means that its reluctance is equal to 0. So only reluctance which will be assumed in this problem is the reluctance of these air gaps. So these number of turns for each winding are given. The width of the gap is also given. Area is also given. The quantities to be found out are the self-inductance of coil N1 and the mutual inductance between coils N2 and N3. So first of all, we will draw the electrical equivalent circuit, and for calculating the self-inductance of the winding N1, we will ignore all the other MMF sources in the system. So only the winding one will be considered, and these are the reluctances of the air gap, since the reluctance of the core is equal to zero due to the infinite relative permeability. So R equivalent will be calculated first, since the source is connected over here. So these two reluctances are connected in parallel and their combination is connected in series. So this will be the R equivalent in this case. And now we will calculate RG1, and it will be given as this number, and RG2 is given as this number. So this is RG3, and R equivalent can be calculated using this combination, and then we can easily calculate the self-inductance of the winding one. Now L11 will be calculated using this expression. Once we have calculated R equivalent, N1 and I1 are given, so phi1 can be calculated, and N1 again is given, I1 is also given, so L11 can be calculated. Alternatively, we can substitute the value of this phi1 in this expression, and here I1 will be cancelled out with this I1, and we will get N1 square over R equivalent. So this is written over here, N1 square over R equivalent. So this is L11. And now in the part B of this problem, we have to calculate the mutual inductance between coils 2, N2 and N3. So the mutual inductance can be calculated by activating either coil 2 or coil 3 and find the flux flowing in the other coil due to the triggered current. So in this case, we will assume that the N3 coil is excited and its effect on the flux through the coil N2 will be calculated. So L23I3 is equal to N2 phi 2. So current will be considered for this coil and the flux will be considered for this phi 2 winding. Okay, so only this source of MMF will be considered, and now the problem becomes quite simpler. So N2 is given to us. We have to first calculate phi 2, and from this figure we can see that phi 2 is actually the flux which is divided uh, from phi 3. So phi 3 is divided between phi 2 and phi 1. So flux divider rule will be applied over here, and phi 2 will be equal to Rg1 over Rg1 plus Rg2 multiplied by phi 3. So phi 3 in this case will be equal to N3IT3 divided by R equivalent, and equivalent reluctance, assuming the source is present over here, can be calculated by the parallel combination of these two reluctances and their series combination with this Rg3. So Rg3 plus Rg1 parallel with Rg2 will be the R equivalent. So now we have calculated R equivalent, and now we have calculated the phi 2, because R equivalent and phi 3 both are available to us, and these will be substituted in this figure. So flux phi 2 will be substituted in this expression. I3 is given and 2 is also given, so L23 can be calculated. So we can either do the cancellations and get the simplified expression before substituting the values, or first calculate all the values of these variables and substitute in this final expression. So this is the final answer which is obtained at the end of this lecture. So I hope you have learned and enjoyed this lecture. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.